lecture,
we will discuss about the chromaticity. It is the effect generated by the quadrupole for the off momentum particles. In last lecture, we have seen the effect of a dipole magnet on the off momentum particle, and a new parameter dispersion was introduced. Now we will see how the quadrupole acts on the off momentum particle, and this effect can generate an aberration, and how that aberration can be corrected. So now we recap the Betatron theorem. Actually, we have an optics, simple optics, in which focusing quadrupole is here, then defocusing quadrupole is here, and again this is repeated. If a trajectory of a particle enters in this optics like this here, so focusing quadrupole will send this trajectory towards the design trajectory, and then defocusing will send it away, and again focusing quadrupole is there, so it will send it again towards the design trajectory, and again defocusing will send it away. So in this fashion, this particle exhibits Betatron oscillations. These are Betatron oscillations of this particle. Here we mentioned that these Betatron oscillations are for the correct momentum particle, means on momentum particle. P0 is the design momentum for which this optics has been designed, and this particle has the same momentum. Now suppose another particle having higher momentum than this P0 enters the optics on the same trajectory, on this trajectory. How the quadrupole will act on this? Now this is the new trajectory for the higher momentum particle. This green one was for the on momentum particle, and this blue is for the off momentum particle. Now for the off momentum particle, because it is having higher momentum, the focal length for the quadrupole will be higher. Means focusing will be somewhat weaker than the lower momentum particle or the design momentum particle. So trajectory will be in this fashion, and then when it reaches to defocusing quadrupole will also act with a somewhat weaker strength. This weaker strength, and then it will send this trajectory towards this. And in this fashion, we can see that this off momentum particle also exhibits a Betatron oscillation, but however with longer wavelength. Means one Betatron wave takes longer length to complete it. Means number of Betatron oscillations in one complete turn for higher momentum particle has been reduced. Means tune, the number of Betatron oscillation in one complete turn, which is known as tune of the higher momentum particle, has been reduced. And as we told earlier that tune is a very important parameter for an accelerator. So tune has been changed, and we have to correct this tune, and how much the tune has been changed and how we can correct it, we will see in this lecture. The change in tune, say this is delta nu, and this change over the unit momentum offset, means del divided by delta. This delta is delta p by p, means fractional momentum offset. So change in Betatron tune over the unit fractional momentum offset is known as chromaticity. This is the chromaticity. It is defined in this way. There will be two chromaticities, one for the horizontal plane and one for the vertical plane. So for horizontal plane, we have to take the delta nu for the horizontal Betatron tune, and for vertical plane, we have to take the delta nu for the vertical plane. So there will be basically two chromaticity. One is the chromaticity X, and other one the chromaticity Y. Now you can see that here, when we increase delta means delta P is positive. Delta P is positive means delta P by P is higher. So for higher momentum particle, delta P is positive, and for that particle tune decreases means delta nu decreases for the higher momentum particle, means delta and delta nu have opposite signs. If delta is plus, delta nu is minus. If delta is minus, then tune will increase and delta nu will be plus. Means chromaticity is a negative number in the synchrotron. This chromaticity has been generated due to quadrupole magnets. If we will see in later part of this talk that there are other magnets which also contribute in the chromaticity, and that contribution can be used for correcting the chromaticity. So the contribution of the quadrupole which generates this chromaticity is known as natural chromaticity. Now suppose this is a dipole magnet. Again, similar picture which we have seen in the case of dispersion. So this is the design trajectory, and design trajectory is for the P0 moment, and this is a quadrupole magnet. Now a higher momentum particle follow this trajectory. It will bend less due to dipole magnet, and it will reach in the quadrupole at the off axis, and quadrupole will focus it. However, had it been a right momentum particle, quadrupole will send it here. But this particle has higher momentum, so it will send the quadrupole sends the particle far away from this. Its focal length will be longer. Now for lower momentum particle, quadrupole will have shorter focal length, so it will pass from here. This is the focal length for the lower momentum particle, and this is the focal length for the higher momentum particle. So we have spread in focal lengths due to delta p by p. Means beam contains a spread in momentum, and then quadrupole will produce a spread in the focal length, and this spread in the focal length was the main cause for generating the chromaticity. Now for off momentum particle, what should be the strength of the magnet? So strength of the quadrupole magnet is defined in this fashion, that is Q by P, which is basically the inverse of beam rigidity, and then G is the gradient of the quadrupole magnet. Quadrupole magnet has the gradient in the field, and this is a constant quantity for the quadrupole magnet. So this G is a constant for the quadrupole magnet. Now in place of P, we have P0 plus delta. This P is the momentum of the particle. It may be the off momentum if delta P is non-zero, and if delta P is 0, then it is the on momentum particle. So P can be written down as P0 plus delta. Again take P0 out, so you will have 1 plus, you will have P0 out, so you will have 1 plus delta P by P0, and this delta P by P0 is denoted by delta. So we have QZ by P0 upon 1 plus delta, and this quantity is again the strength defined for the design moment. Actually, when we say strength of the quadrupole, we refer to this K0, and this K0 is divided by 1 plus delta. So for higher momentum particle for which delta is plus, this K is smaller than K0 for plus delta, and K is higher for K0 for minus delta. So quadrupolar kick has been reduced for the higher momentum particle. You can see, and you can calculate the quadrupolar kick using this formulation. Now if chromaticity has been generated, is there any reason that we should correct it? What are those reasons for which we should worry about the chromaticity? So one reason is the spread in the betatone tune itself. Betatone tune is an important number, and it tells how many oscillations are there in the one complete turn. So if there are some imperfections in the machine, So far we are studying about the perfect machine, means each dipole magnet is perfect, each quadrupole magnet is perfect, and those are placed according to our wish, means there is no misalignment in the magnets. In real practice these errors are there, and when these errors are there in a synchrotron, these error also occurs in each turn, means particle will see these error on each turn when it passes through that magnet which is having error. So error is also periodic in nature in the synchrotron. So particle is exhibiting a betatron oscillation and it is subjected to some periodic forces. So an oscillator, when it is subjected to some periodic forces, it can, this periodic force can excite some resonance in that oscillation, and that resonance may cause the growing of the amplitude. In the similar fashion, betatron oscillations can also subjected to some resonances due to imperfections, and amplitude of betatron oscillations will grow over turn by turn, and ultimately the amplitude will reach to the wall of the chamber and particle will be lost. So these are the resonances which depends on what the frequency of the betatron oscillation is there, and that betatron oscillation frequency is related to tune. That's why tune is an important number. Tune defines whether the resonance can occur or not. So this is very first reason we had to be careful when we talk about the chromaticity. The second major reason for correcting the chromaticity is head-tail instability. Actually, in accelerators, when we store the charged particle beam, there are various types of instability which can occur, and these instability can cause the beam losses. And one type of those instabilities is known as head-tail instabilities. In this type of instability, the head of the bunch drives some resonance kind of phenomena for the tail, and in this fashion beam loss can occur. To avoid that kind of instability, chromaticity has to be made 0. So these are two reasons for which we have to correct the chromaticity. Now how to correct the chromaticity? Here we have seen that quadrupole is having larger focal length for the higher momentum particle up to this, and shorter focal length for the lower momentum particle. If we want to correct the chromaticity, we have to make sure that focal length for these particles must be the same. Means focal length of higher momentum particle should be decreased and focal length for lower momentum particle should increase. And how we can do? We can consider that there is some focusing lens which focuses the higher momentum particle. So instead of reaching there, these particle reaches here. And for the lower momentum particle, we need a defocusing lens. So this should be a defocusing lens. So it defocuses and focal length increases for the lower momentum particle, and then both the particles having higher momentum or lower momentum reach to the same focal point. So in this fashion we can correct the chromaticity. Means on one side of the axis we need focusing lens, and on other side of the axis we need defocusing lens. And one thing is here, you can see that in case of higher momentum particle, we need to exert a kick in this direction, because we have to change its path from red orbit to blue orbit. So kick should be in this direction by this magnet. For lower momentum particle also, we should have the kick in the same direction, because now on this side for lower momentum particle, this magnet should act as a defocusing lens. And note one thing, that when we are talking that all the positive momentum particles are there and all the orbits of negative momentum particles are there, it means orbits corresponding to these momentum have been separated out. Means we are talking about the region where dispersion is non-zero. If dispersion is zero, these orbits will not be separated out and we cannot correct the chromaticity. So for correcting the chromaticity, we need some dispersion, and at the location where dispersion is non-zero, this kind of optics has to be inserted. Now how this optics can be realized? Means one side is focusing and other side is defocusing, or you can say that on both sides kick is in the same direction. Now consider again the field of a quadrupole magnet. Field of a quadrupole magnet increases linearly with x. This is the vertical component of the field which is drawn here, and this is the horizontal displacement from the design axis. So field linearly increases in the case of the quadrupole magnet. Because it is linearly increasing, gradient is constant. Now required field for chromaticity correction. Actually we have seen that B, vertical component of the magnetic field, at plus x should be equal to at minus x. Then only kick will be in the same direction. So field should be even. Now we compute the quadrupole kick for the off momentum particle. Quadrupole kick is given by KLX, and already we have seen that this K for the off momentum particle has to be replaced by K0 upon 1 plus delta. Lx is there. Now we have introduced one approximation that energy spread or momentum spread is not large enough. Means this delta P by P is small than the form. Then this 1 plus delta can be approximated by 1 minus delta in the numerator. Because when it will go in the numerator, it will have 1 plus delta raised to power minus 1. And when we use binomial expansion for this and retaining only first term and rejecting the higher order term due to this approximation, we will have 1 minus delta. So we have K0 Lx minus K0 Lx delta. Now you can see that this is the normal quadrupole kick. Let it be a right momentum particle, the quadrupole kick should be K0 Lx, and this is there. And this kick is due to delta. If delta is 0, this kick will be 0. Means this is for the off momentum particle, and it varies as x into delta. Now you can see that where the dispersion is non-zero, you can have x is equal to d by delta, which we have seen in lecture on the dispersion. So delta can be written down using this d upon x is equal to d delta. So delta can be written down x over d. Now this quantity, if we will put x into delta is equal to x into x by d, means this quantity varies as x square. Means the field should be even and it should vary with x square. Means this should be the field profile like this. Now if we go in the minus side or plus side, by has the same sign, means it will kick in the same direction, and variation in the by is with square, means it is a parabolic. This type of required field can be generated using the sextupole magnet, means 6 poles, and this magnet can produce the required magnetic field.